When a fuel rod comes out of a nuclear reactor, it has just spent 5 years splitting uranium atoms. It's now around 300 degrees Celsius. It's radioactive enough to deliver a lethal dose in seconds, and still generating heat from radioactive decay at a rate of about 10 kilowatts per assembly. You can't put it in a container. You can't ship it anywhere. If you turned the cooling off, it would melt itself in days. So the first thing engineers do is drop it into water. Specifically, a 40-foot deep pool lined with stainless steel, packed with neutron-absorbing boron, and circulated continuously through heat exchangers. The water does two jobs at once. It pulls the heat away, and it shields the radiation. Stand at the edge of one of these pools and look straight down at fuel that could kill you in 30 seconds, and you'll receive less radiation than you would on a transatlantic flight. That's step one. The fuel will sit in that pool for the next 5 to 10 years before it's cool enough to even consider moving. This is how nuclear waste management actually works, and the engineering only gets more extreme from here. To understand why nuclear waste is so difficult to deal with, you have to understand what spent fuel actually is. A fresh fuel assembly going into a pressurized water reactor is essentially a bundle of zirconium alloy tubes filled with ceramic uranium dioxide pellets, inert. You could hold one in your hand. After 5 years inside a reactor core, that same assembly contains over 300 different radioactive isotopes, including plutonium, cesium, strontium, and a long list of others that did not exist before they were created by the fission process. Some of these isotopes will be dangerous for decades, some for thousands of years, some for hundreds of thousands, and every operating commercial reactor in the world produces about 20 to 30 tons of this spent fuel every year. So the question becomes a practical one. What do you actually do with it? The answer engineers have settled on is a process that takes the waste through a series of stages, each one designed to handle the fuel at a specific level of intensity. The pool is stage 1. It exists because the fuel coming out of the reactor is too hot, both thermally and radiologically, for any other form of storage to work. Inside a typical spent fuel pool, water temperature is held below 65 degrees Celsius by the cooling system. The pool itself is reinforced concrete several feet thick, lined with welded stainless steel to prevent leaks. The water is treated with boric acid, because boron is one of the most effective neutron absorbers known. This is critical, because if the fuel assemblies were placed too close together without absorbers, the residual neutron flux from the spent fuel could potentially restart a fission chain reaction. Engineers solved this by spacing the assemblies in racks with neutron-absorbing panels welded between them. For the first year after a fuel assembly leaves the reactor, decay heat drops by a factor of 100. By year 5, it is dropped by another factor of 5. By year 10, it is dropped by another 40%. This is the curve engineers are waiting on. The fuel has to cool slowly, and there is no way to speed it up. Active circulation pumps move the water through ion exchange resins and heat exchangers continuously, around the clock, for years. If that cooling system ever fails, the situation becomes serious quickly. This was one of the central concerns at the Fukushima Daiichi spent fuel pools after the 2011 earthquake. A pool that loses circulation will heat up, the water will begin to boil off, and if it ever fully drains, the exposed fuel can catch fire and release radioactive material directly into the atmosphere. The pool is not just a storage container. It is an active engineering system that has to keep working. After 5 to 10 years, depending on the burn-up history of the fuel and the regulatory requirements of the country, the oldest assemblies in the pool are ready for the next stage. They are still extremely radioactive. They're still generating heat. But they are now cool enough that the heat can be removed by passive air convection alone. No pumps, no water, no power. This is where dry cask storage comes in. A dry cask is one of the most over-engineered objects in industrial use today. The basic design is a steel cylinder, several inches thick, welded or bolted shut after loading. Inside, the spent fuel assemblies sit in a basket structure that holds them in fixed positions. The interior is filled with helium, an inert gas that prevents corrosion of the fuel cladding, and improves heat transfer. Around the steel cylinder is another shell of either steel or concrete, typically 30 inches thick, that provides radiation shielding for anyone standing nearby. A loaded cask weighs around 150 tons. To get certified by the United States Nuclear Regulatory Commission, every dry cask design has to survive a brutal series of tests. Engineers ram them into concrete walls at highway speeds. They drop them from cranes onto steel spikes from heights of 30 feet. They submerge them underwater. They set them on fire at temperatures over 1,400 degrees Fahrenheit for 30 minutes straight. The cask has to come out of all of this with its containment intact. Not slightly damaged. Intact. Once a cask is loaded and sealed, it gets placed on a concrete pad outside the nuclear plant. It sits there. Air convection moves heat out through ventilation channels in the outer shell. There are no moving parts, no power required. The cask just sits, year after year, doing its job by being well designed and very heavy. Right now, in the United States alone, there are roughly 90,000 metric tons of spent nuclear fuel stored this way, across more than 70 sites in chain-link enclosures at the same nuclear plants where the fuel was originally used. Most of these casks are well within their operational lifetime. They are rated for around 100 years, but the waste inside them stays dangerous for 10,000. This is where the temporary engineering ends, and the real problem begins. You cannot leave nuclear waste in dry casks forever. The casks themselves will eventually corrode. The plants will eventually be decommissioned. The institutions managing them will change, merge, dissolve, get reorganized. Over the time scale that this waste remains hazardous, every political system currently in existence will rise and fall multiple times. The casks were designed for a specific job, and that job was buying time. The actual solution, the one engineers settled on after decades of research, is to bury it. But not just bury it. Bury it inside a multi-barrier isolation system, in geology stable enough that the engineering itself becomes secondary to the rock surrounding it. This is the deep geological repository concept, and the principle behind it is straightforward. You don't trust any single barrier. You stack them. 5 barriers, each independent, each capable of holding the waste on its own. The probability of all 5 failing simultaneously becomes vanishingly small. If you're following along, you might be wondering why this hasn't already been solved everywhere. The answer is that it has been studied for decades in the United States, the United Kingdom, France, Germany, Sweden, Canada, and Japan, and almost every program has stalled at some point. Yucca Mountain in Nevada was selected by Congress in 1987, studied for decades at a cost of over $9 billion, and then defunded in 2010 over political opposition from the state. The United Kingdom's repository project, estimated at £54 billion, was graded as unachievable by Treasury reviewers in 2025, citing major issues with project definition, schedule, and budget. Germany has wrestled with site selection for 50 years. Only one country has actually built it. If you're finding this helpful, hit subscribe. I cover engineering deep dives like this one every week. Now let's talk about Onkalo. On the western coast of Finland, on a small forested island called Olkiluoto, there is an elevator that descends 430 meters into the bedrock. The journey takes about 5 minutes. At the bottom, you step out into a network of tunnels that has been under construction since 2004. The walls are exposed granite, gray and pink, fractured in places, smooth in others. This rock is 1.9 billion years old. It formed before complex life existed on Earth, and in that entire span of geological time, it has remained essentially stable. No major fault movements, no significant groundwater intrusion, no deformation. This is the host environment for the world's first permanent nuclear waste repository. The facility is operated by Posiva, a Finnish company jointly owned by the country's 2 nuclear power utilities. Construction has been underway for over 2 decades. The total tunnel network, when complete, will stretch around 70 kilometers. The repository will hold 6,500 tons of spent nuclear fuel. The Finnish regulator is expected to grant the operating license soon, after which the first canisters will go in. And the canister itself is a piece of engineering worth understanding in detail. Each Onkalo canister, is 5.2 meters tall and weighs 25 tons fully loaded. The interior is a cast iron insert, machined with channels that hold exactly 12 spent fuel assemblies in fixed positions. Surrounding that cast iron core is a 5 centimeter thick shell of pure copper. Not a copper alloy. Pure copper. The two layers serve different functions. The cast iron provides mechanical strength to handle the weight of the rock and the pressure of the surrounding clay. The copper provides corrosion resistance. Once a canister is filled, the lid has to be sealed. This is where one of the more elegant engineering choices comes in. The seal is created using a technique called friction stir welding. Originally developed in the 1990s for joining aerospace aluminum, friction stir welding doesn't actually melt the metal being joined. Instead, a rotating tool plunges into the seam between two pieces of copper, generates heat through friction, and stirs the softened metal until the two pieces become metallurgically continuous. The result is a weld with almost no defects, no porosity, and no introduced impurities. For a container that has to stay sealed for 100,000 years, conventional welding wasn't good enough. Now, the choice of copper itself is one of the most counterintuitive decisions in the entire facility. Copper isn't a strong metal. It isn't a high-tech alloy. It's the same material in pennies and plumbing pipes. But the engineers at Postsiva and their Swedish counterparts at SKB chose it for a very specific reason. In the right environment, copper does not corrode. Archaeologists have pulled copper artifacts out of anaerobic clay deposits in Europe and Scandinavia that have sat untouched since the Bronze Age, more than 3,000 years ago. The metal comes out essentially unchanged. The reason is that copper corrosion requires oxygen. In an environment where there is no dissolved oxygen in the surrounding water, the chemical reactions that normally degrade copper have no fuel to run on. They stop. So the engineers asked themselves a simple question: what if we don't try to invent a new material, and instead reverse engineer the conditions that nature has already proven can preserve copper for thousands of years? This is what Onkalo actually is, not a vault, not a tomb in the cinematic sense. It's an environment, deliberately constructed, designed to mimic the chemistry of an anaerobic clay deposit, scaled up to industrial size 400 meters underground. To create that environment, the canister cannot just sit in an empty hole. Around it, engineers pack rings of compressed bentonite clay. Bentonite is a naturally occurring volcanic clay, mined from deposits in Wyoming, India, and several other locations. Its key property is that it expands dramatically when it absorbs water. Compressed bentonite, when wet, can swell to 7 times its dry volume. Once it swells, it becomes nearly impermeable to water flow. The clay does 3 jobs at once. It mechanically stabilizes the canister, holding it in place inside the deposition hole. It chemically buffers the environment, regulating pH and consuming dissolved oxygen, and it physically blocks groundwater from reaching the canister surface. If the surrounding rock ever shifts and a fracture opens up nearby, the clay will swell into the gap and seal it. This is called the self-sealing property, and it is the reason bentonite was chosen over any other buffer material. Above the canister, the deposition tunnel is also backfilled with bentonite. The tunnel itself is sealed. The access shafts are sealed. By the time the facility is full, around the year 2120, every part of the underground network will be filled with clay or rock. There will be no air spaces, no voids, no internal structure, just sealed canisters surrounded by clay, surrounded by 1.9 billion year old granite, with hundreds of meters of stable rock above them. That's the multi-barrier system. 5 layers, working together. The first barrier is the ceramic uranium dioxide pellet itself. Ceramic is chemically stable and binds most fission products into its crystal structure. The second barrier is the zirconium alloy fuel cladding, the original tube that holds the pellets together inside a fuel assembly. The third barrier is the cast iron insert inside the canister. The fourth barrier is the copper outer shell. The fifth barrier is the bentonite clay buffer. And then surrounding all of it is the natural barrier, the bedrock itself, which has held its position for 1.9 billion years, and is expected to continue doing so for at least the next 100,000. Even if 4 of the engineered barriers somehow fail, the fifth holds. Even if all 5 fail, the rock is the final defense. The engineering philosophy is paranoid in the most productive sense of the word. It assumes everything will eventually break, and it stacks redundancies until the probability of complete failure is mathematically negligible. But there's one final problem that Onkalo has to solve, and it has nothing to do with metallurgy or geology. It has to do with people. 10,000 years ago, humans were just inventing agriculture. 5,000 years ago, the first written language was emerging. 1,000 years ago, English as we know it didn't exist. The waste inside Onkalo will be dangerous for 10 times longer than English has been spoken. There is no way to predict who will be living near the site, what they will know, what languages they will speak, or whether they will recognize any warning sign we put on the surface. This problem has occupied a strange branch of engineering called nuclear semiotics. Linguists, archaeologists, and materials scientists have been working on it since the 1980s. The challenge is to design a marker system that communicates one specific message across deep time. This place is dangerous. Do not dig here. Proposed solutions have ranged from massive granite obelisks inscribed in multiple languages to fields of jagged concrete spikes designed to look universally menacing, to genetically modified cats that change color in the presence of radiation, paired with folk songs designed to spread the warning through oral tradition for centuries. None of them are perfect. The current consensus is that any marker system needs multiple layers of redundancy. Buried libraries, surface monuments, archived records distributed across institutions worldwide. Even the messaging itself has been carefully designed. One proposed inscription, developed by a team at Sandia National Laboratories, reads in part, "This is not a place of honor. No highly esteemed deed is commemorated here. What is here was dangerous and repulsive to us. The danger is still present, in your time, as it was in ours." Whether anyone in the year 12,000 will be able to read it remains an open question. Right now, around the world, the rest of the global nuclear industry is watching Onkalo carefully. Sweden is building its own repository at Forsmark, using essentially the same KBS-3 canister design that Finland uses, and started surface preparation in 2025. Canada selected the Wabigoon Lake Ojibwe Nation and the township of Ignace as host communities for its repository in November 2024, with construction expected to begin after regulatory approval. France is building Sigio, a clay-based repository in eastern France. The United States is back to evaluating multiple potential sites. Globally, around 400,000 tons of spent nuclear fuel currently sit in temporary storage. Estimates suggest that to safely dispose of all of it would require roughly 60 facilities the size of Onkalo. The engineering for that scale of construction has, in a sense, just been proven possible. What makes nuclear waste storage genuinely insane from an engineering perspective isn't any single component. The pool is well understood, the cask is well tested, the canister is precisely manufactured. The bedrock has been geologically stable for nearly 2 billion years. What's insane is the timescale. No other field of engineering routinely designs systems that have to function for 100,000 years. Bridges are designed for 100 years, skyscrapers for 200 years. The pyramids, our most durable surviving structures, are around 4,500 years old. Onkalo has to function for more than 20 times longer than that while sealed, unmonitored, and ultimately forgotten. The engineers building it accepted that constraint and worked backwards from it. They couldn't rely on monitoring. They couldn't rely on maintenance. They couldn't rely on institutional memory. So they designed every component to fail safe, in geology that doesn't move, surrounded by a chemistry that mimics conditions nature has already proven can preserve materials for millennia. It is one of the most ambitious problem-solving projects our species has ever attempted, and the reason most people have never heard of it is that, when it works, nothing happens. Forever. That's the entire goal. I'll see you in the next one.